Hello everybody, it's been a little over half a year since my last video. It's time for an update. And so last that we were covering was how I was feeling the capelling process. Reason I believe was the amount of silver that was in the process. The silver bar itself had some sand in it, as well as the lead that I was mixing it with was from recycled from a construction site. So it too was really fully loaded with sand. So all that sand together, I couldn't even clean it all out. I couldn't get it out. So I ended up creating what I believe was a glassy layer surface on the bottom side of the material, just not allowing the compelling material to compel the oxides away. So I've been switching over to the nitric acid process, using nitric acid to dissolve and then re-solidify it out of the solution. So that's what I've been up to lately, and so I'll give you a quick little view on how we do this process. So we're going to be dissolving some silver. We're going to be using that 999 that we got from our trusted bullion provider. So once you're done finishing reacting the acid with the silver, then you can remove the solution from what is remaining. The color usually indicates what is contaminating the silver. If it was pure silver, it would just be clear. So now that we remove the silver from the solution, we're going to now cement the copper from the solution. So we just take some copper, dump it in. And then after a bunch of hours have passed, what you get is this really cool cementing of silver onto the copper. It looks amazing. And after doing this a couple times, I've been convinced now that I want to make a Christmas tree with this branches looking like this and this kind of finish. So while I've gone the route of the nitric acid method, even though it's the only method I could take right now, there is some advantages and disadvantages compared to the cupellation process. The disadvantages is that it's a little more complicated and it does take up quite a bit more time to do it. But if it comes to consumables and I can make my own consumable, well, that's pretty nice because I don't really want to keep buying lead and doing this process consuming the lead as it's not recoverable. But I also do have quite a bit of silver-plated items that I need to process, and the cupellation process is just not meant for that. So I'll be able to use a nitric acid to peel off the plating off of these items and process it that way. When I was doing this process, I came across the issue of trying to make it more efficient, as the video I'm about to show you is just not able to make enough for me. So here we have a Berkland's Eye reactor made by 2 Mason's jar, black silicone sealed to a melamine covered particle board, feeding down into another mason jar. It's not working right now because this thing's actually not even functioning properly. I don't use it anymore, so yeah. It's not sealed anymore, but this is just for a demonstration. Yeah, I don't even use this thing anymore, and it's powered by 2 oil burners. So this makes for a great example of how not to make a Berkland's Eye reactor. Not because of the materials used, other than the power supply used. These things cannot actually support the amount of power that you are looking for. Those arcs, they can be pretty long, but they don't have the amperage to really put the energy into the air that it's pyrolyzing. So they're like little candles. Like I could touch this. After a while it'll get a little warm, like the top will get really hot. But yeah, during the summer the rest of the glass might be too hot, but as you can see, for the most part, it will hold up okay. It's fogged over now after so much use, and it has aged a little now. So you can see like the little
heat marks from the candles of electricity. So yeah, don't make it this way.
So when I learned that you could use nitric acid to refine the silver, I thought that was awesome. I got another option that I could do. But the issue with this plan now is that it cost me about $40 a liter before even shipping just to get my hands on some nitric acid. So if I wanted to take this route, it'd probably be best to make it myself. So that's when I had to go online, and then I tried to start learning the exciter circuit and then come to the conclusion, you know what, it'd just be easier to buy a module myself. It'd save me a lot of hassle. Then I found this module here on Plasma Channel. And once I got my hands on this, I'm like, okay, just shove it into the tube, game over, I'll win. But as you can imagine, that didn't go over too well. The arc destroyed the tube in just seconds. But also, I learned something else very important at that time, and that these modules just can't sustain running for anything really longer than a minute before the parts on the chip start to melt down. So I had to think of some kind of solution that is sustainable to run 24/7. And so that's when I just went back to the original example that I saw, just recreate what I saw there and try and improve on it. And so that's when I made the apparatus you just saw. So after building the apparatus and running it for a few weeks, it was quite clear that it wasn't going to produce the quantities I need in the time that I needed, as it would take probably about a week just to produce a quarter liter. So if it took me a month to produce a liter, yeah, that's just not going to suffice. So trying to look up for other ways to improve the process, came across the Jacob's ladder. And it turns out that this actually, instead of improving the situation, it actually made it worse. As you can see, I've acquired some salts here, and even though I wasn't really following the scientific method, um, this higher quantity was produced without the Jacob's ladder, and I was able. I only produced less nitric acid salts while using the Jacob's ladder. So um, to me, it didn't look like the Jacob's ladder was helping at all. But so then, what else could I do to make this situation better? And so, make more chambers. And so that's what I tried doing. But while in the middle of that process, I just asking myself, is this really the way to do it? Well, then I started looking at the process itself. So here is the picture of the molecule we're trying to construct. Hopefully it doesn't look too complicated. We're going to be able to synthesize this from air and water. The first half being the NO2. We're going to be using the electricity and the air itself to construct it. And then we'll pass that gas through the water, which will obtain the last OH molecule part that we'll be looking for to complete our acid. So we need to start by fraying the bonds between the nitrogen in itself and the oxygen in itself. And to do that, we're going to need to heat up the gas to at least 1500 degrees. Anything above that, that's great. We can increase the velocity of air through the point of paralyzation, but we do end up hitting a point of diminishing returns. A simple everyday today example of where we see this kind of process happening is in internal combustion engines, as they typically operate within these ranges as well. They produce nitrous oxide, but while the gas is on its way out, it gets corrected by the catalytic converter to revert them back into N2 and O2. So now that I'm trying to go out and beyond what was already well established, and mind you, at this point, I am thinking ahead and thinking, do I need to go in the route of using microwave transformers? That was something I really didn't want to do because I'm aware of their notorious reputation for, people killing themselves while working with them. So I wanted to try and avoid this as a last resort. So going through forums and such, it didn't seem like anyone had the whole picture. Maybe everyone had maybe just a little bit of the picture to themselves. Though, and despite that, there was one person that got the whole picture. But this one person was many steps ahead of everyone else and just wasn't really good source for information to pull from. But I'll still put a link to his video in the description. Otherwise, now that we know the temperature that we're trying to hit, we just need to create the hardware to do so. And if we want to carry forward, we are also going to need to understand a bit about electricity. So here I'm showing you what you can consider the triforce of electricity. On top, we have power denoted by the capital letter P, and it is the product of both the voltage and amperage. Voltage being denoted by the capital letter V, and amperage being denoted by the capital letter I. And so voltage is the parameter that's going to allow electricity to jump through the air. Increase the voltage, the longer the arc can be. The I, the amperage, is going to pretty much tell you how thick that current is how many actual electrons are flowing through that space in that given time. So when I first started this, I was actually incorrect on what is actually the half that is important. I originally thought it was going to be the voltage, but after when I came across the whole temperature orientation of this whole problem, then I quickly realized it's not a voltage thing, but an amperage thing. So with that in mind, I take to the forums to see if there's any leads I could follow, but while doing so, there was a lot of talk about the actual arc itself and how the voltage is not really a necessity on maintaining the arc once it's been established, and it could be held just by the amperage if the voltage can be maintained at least about 100 volts. But I don't like this idea because this requires you to strike the electrodes in some way to get a spark or some way to initialize the circuit before you pull the electrode apart so you can establish a nice long arc. So take it as you will. I don't like this idea. Like for example, if something were to ever happen to your power and it gets cut out to your apparatus, it's not going to turn back on once the power returns. So I like the idea of having something that's maybe a little less tentative. So while I'm following the leads on the forums, I come across the next subject, which is arc welders. And to initiate the circuits for those arc welders, I was thinking I was going to be clever and using one of these piezo strikers that you could find in a barbecue lighter. These things come with a 14,000 volt dielectric strength within the crystal. So these things are actually quite compatible with these kind of circuits. But as you can see, this little device thing is quite small and finicky, so I was thinking, oh, okay, then I'll just use this thing and it'll solve my problems, right? But this thing is actually more like this thing in disguise. So it works very differently. And so what ended up happening is that I ended up frying this device because electricity actually worked itself backwards into it and just destroyed it inside out. So that had to be scrapped. Then there's the extra case of highly specialized MIG welders that are made for sheet welding. And yeah, those things cost several $1,000s, and in the end, they still may not be the most suitable power supply for what you need them for. Another thing that was coming up across a lot in the forums was that a lot of people were just not understanding what is the target temperature that they were trying to hit. There was a lot of confusion that 3,000 degrees is the target temperature. Some people think it was 10,000 degrees. And I don't really blame them too much because when you're looking at the atoms and specifically the nitrogen, how it has a triple bond, it's kind of notorious for having a really strong attraction between the two nitrogen atoms, and that why people I think are getting confused is that it requires a large amount of energy to dissociate the nitrogen bonds completely. But that doesn't seem to be the case, as explained in the previous slide about how internal combustion engines in cars could also achieve the same thing. So that is a misconception debunked. So now with the arc welding lead gone, there's only one lead I have left, and it's the one I was trying to avoid, and that is microwave transformers. Microwave transformers typically reach around 2,000 volts. So I was thinking, like, am I going to have to rewire this thing to try and achieve like the 10,000 volts that I'm looking to acquire? Well, that doesn't actually seem to be the case because I came across the game changer that I was looking for, and that is this. So this is what is called a voltage multiplying circuit. What it's able to do is take an AC signal and multiply it several times to produce a really high voltage DC spark. But all the illustrations on the internet doesn't quite tell you how to properly use this circuit. So when I started implementing this into my own apparatus, there is a fine print that you will need a load with the gap because the gap itself is not a load. And so if the circuit ever closes, the flow of electrons is so that it would rip out the dielectric strength from the last diode, even two. I've had two fail in one go. So I had to figure out what to put as a load along with the arc gap. And the best solution for that would be putting inductors there. So now that we know all the parts that we're looking for to construct this circuit, that is one high voltage diode, one high voltage capacitor, and one inductor to go along with it to make each stage of the voltage multiplier. And all of these parts can thankfully be found within the microwave itself too. You'll be able to find the high voltage capacitor and the high voltage diode grounding that capacitor to the chassis of the microwave. And if you happen to be in the spirit like I was for scrapping microwaves, I strongly suggest for you to grab one of the power cables as well as help you rig up the apparatus much quicker than having to come up with a solution yourself. And so with all that said, I made this.
So here we have my second generation Birkeland reactor. It looks quite complicated, but let's go through this to better understand exactly what's going on. We got this half going for this reactor, and then we're going to have this half going for this reactor. The beginning of the whole apparatus starts over here. We got power coming in from the wall. It comes in through a dimmer switch. This dimmer switch doesn't seem to work for me like it intended. I did have one previously that did work, and then I burnt it out. And then working with this one, it seems to only act as a binary switch. So if you end up trying to copy me or whatever and decide to use a dimmer switch yourself, you might end up having better luck with me to help fine-tune setting up your apparatus. And then so coming through the switch, we come into the heater. The heater acts as a ballast, restricting the electricity flow from reaching the full power from reaching the two supply transformers, because if I didn't have the heater, we would see 12.5 to 13 amps being fed to the transformers. As you can see here, we only get about 4 to 4.5. Both transformers are also wired in series. Again, this is for power control. If I only had one on the circuit, too much power would be fed to it, that the transformer would be overheating, the electrodes would be eroding too fast. So having two on the circuit dissipates the wear and tear on the system, as well as the dissipation of heat is better. So two are on the circuit. So let's go down one side. So we got this supply transformer feeding into the capacitor bank, the capacitor bank going into the reactor doing its sparky thingy, coming in, and then coming into the four inductors that are wired in line, and then into the leading capacitor again. So same thing for this side. We got the capacitor bank, we got it feeding into the reactor, and then we got it feeding into the four inductors, and then back to the leading capacitor again. And then as for the air, we got ourselves a little air pump in the back. It's also actually hooked up to an oxygen concentrator that has a hose going down and underneath the table. That's there to help with the air pressure, because this sometimes could, the ceiling is just not that great sometimes, so it could use a little extra pressure to feed into the water bottles. So yeah, it comes in through the two gas tubes and then into the mason jars, which also I need to replace with a better solution because the steel lids on these things are dissolving into the acid. So that needs to be switched up with something better. We got a little fan here for cooling because the lids on these lunch boxes have a little silicone gasket. So I need to cool down the chambers to keep the gaskets from melting away and, breaking that seal even worse than it already is. So as for the electrodes, those are actually just plain steel electrodes. I managed to bring down the power consumption enough in this device that there isn't enough power that's deteriorating the electrodes. At least a whole lot. There is a tiny bit. It's pretty tiny. I have to switch the wires back around with the positive and ground because the ground side is actually the side that corrodes, not the positive. So to keep the electrodes at relatively equal lengths, I have to switch the wires every once in a while. I do have these stainless steel rods that I could use for electrodes, but then I would have to use these rubber stoppers as mounts, and I'm not a fan of that. It's pretty sketchy. With this kind of power, I don't want to risk it falling out or touching the chamber or something like that. So I think if I end up having to replace the electrodes, I think I'm just going to stick with the same solution I have, and rather than trying to step up to a more heavy duty solution. Though I'm not completely out on this yet because maybe I do want to pump more power for experimental situations. But as it is right now, I'm happy with the setup I have now. I just want to keep it working as it is. Don't want to tamper with the setup too much because I do need this nitric acid. So yeah, this setup could fully run 24/7 nonstop, which was something of an issue that I found seeing other people's examples because they don't even say anything on their little 1 minute clip, so you don't get any details. And now maybe that you see what I made here, you will know better yourself too that a lot of the other examples you will see just can't sustain operation for anything longer than maybe a minute or two before something overheats. But this setup is fully able to manage itself. You could just power on and forget. This is the whole reason why it took me much longer than expected for this video to come out. I thought it was just going to be the first generation Birkeland's eye reactor, then this whole thing stretched away out for many more months. But at least now I have something that I'm more proud of to show you and actually contributes to the whole community rather than trying to just get show off credit only. So hopefully this will help you in you supplying yourself with your own nitric acid if that's what you need. Don't make these little... Actually, you know what? The first generation cost me same amount to build as it took me to build all of this because this takes about 10 microwaves, and if you're spending about around $0 to $20 per microwave, those microwaves cost about the same amount that it took me to purchase those two oil burners. So it's pretty equal, but at least one's competent at producing what you need while the other one is more for show off on a YouTube video.